Welcome to the third and final video in the 13th chapter of the Crystal Clear Electronics curriculum. In the first two videos, we collected all the electrodynamics topics needed to understand how motors work. With this knowledge, we built a DC motor with a commutator and brushes. We also understood the role of the stator and the rotor in generating the torque of the motor. Now, let's see this all in practice.
Here you can see our little mock-up made by Dani. It is a working motor made in a way that everything looks good. Can you tell us what these two magnets are for?
Of course! At the two edges, we can see the permanent magnets that generate the stator's magnetic field.
Yes, these are permanent magnets. We can imagine them as lines of force that go from one magnet to the other, but unfortunately, they are invisible. The important thing is that the coils of the rotating part are in this magnetic field. Am I correct?
Yes, that's correct.
And let's talk a little bit more about the fact that there are 4 coils here. Why not 2? Why 4?
Yes, as mentioned previously, having more coils in the engine helps it rotate more smoothly. This is because having only 2 coils can cause the motor to jump sporadically, whereas with more coils, there is always sufficient torque to keep the engine running smoothly.
So what you're saying is that it would work with 2 coils, these 2 specifically.
It would work, but it would be jerky.
It might be uneven. Let's also show that there is a state where, we've talked a lot about this, there would only be 2 coils, then there would be a state where there is no torque on it, which is, in my interpretation, the state where the loop is like this. Then, there's a force like this on one, and a force like that on the other, and it won't rotate. Torque only exists when it is turned a little bit out of this state. The maximum torque on these 2 coils is when they are perpendicular to the magnetic field. I got it right from the curriculum, didn't I?
That's all correct. It also clarifies the phenomenon that when you plug it in, it may not start by itself and might need a little push. It happens because when you plug it in, the magnetic field may not be strong enough to generate the required torque to start the movement.
Can we demonstrate this? Please plug it in. And we can see that nothing happens, but if you push on slightly, it starts rotating. We said that there's a concept here called angular momentum. So now the rotating part has angular momentum, which helps it always swing through that dead point when there's no torque on it. Then, it swings through on its own, and then, suddenly, it's got torque again. And to be sure that it always gets torque in the right direction, it's a homemade commutator made of a spring, another spring, and some very flimsy wire. Well, it's worth taking a closer look at it. The point is that the commutator always switches the voltage to the coils in a different way, always in reverse, 180 degrees. Now let's move on to a motor that works and is a shop-bought machine. You could see this edging mower in action in the previous video. You can see the motor laid out in parts here. Starting from this direction, you will notice an axle stub that has been sawed off. We can remove the rotary movement from this shaft joint. It's built in like this. This little black part is interesting because it's crucial to consider how the motor is attached to the structure you're using it in. The stationary part of the motor is, of course, bolted to the structure. So that's how they were put together. And inside the stationary part, can you show it to the camera please? There are 2 little magnets inside. They interact with the rotating part. The rotor, in this case, is already a baked rotor. That's why the coils are black instead of copper. That's where it takes up space. And what you can see is a tiny plastic part. That's actually a fan that has melted due to the heat. But you can see there are little gaps in the side of the housing. That tiny part rotates, mixes the air, and gets it into the motor, cooling it. And finally, there's the commutator, which we said is the heart of the motor. Without it, the motor couldn't work. The commutator has springs that hold the brushes in place, and if you look at the brushes, you can see that they are fairly new brushes, so they're not very worn out. So there must be some other malfunction causing this motor to stop working. Well, it's got a burnt winding in it. So that's how this little motor is put together. It has the same structure as this sling bar model or the first DC motor created by Ányos Jedlik. So the structure hasn't changed much. Once again, we have the opportunity to see our structure in pieces.
Now that we have looked at the motor components in more detail, let's move on to the next topic.
Okay, we can now build upon our previous knowledge of DC motor control with some basic concepts. We will be focusing on 3 main points. Our first question is how to control the speed and torque of a DC motor. Secondly, we will introduce the issue of AC voltage-driven motors. It is vital because in households we don't have direct current. We have 50 Hz, 230 volt voltage in the sockets, which we use to power our motors efficiently. Thirdly, we will look at a relatively common type of motor that doesn't need a mechanical commutator.
So, let's look at the question of speed and torque.
Speed of a permanent magnet DC motor is proportional to the applied voltage, and its torque is higher when the current through the windings is higher. The direction of rotation can be changed by switching the polarity of the supply voltage. It is essential to adjust the motor within the limits set by the manufacturer to avoid causing any damage. These limits are usually provided on the side of the motor or through a type number that we can use to find the necessary information on the internet, such as the maximum voltage and power. Those who are smart and remember the previous chapters might know that it is also possible to calculate the permissible current from these values. It will provide data that is close to the actual values. In the past, horsepower was used as a unit of power.
An easy way to illustrate how to set the speed with voltage is to take the fan in your kit and supply power to it from a lab bench or even a self-bit potentiometer voltage divider. We will show you how to do this using a slightly larger motor.
Please set the speed to a low level. Increase the voltage gradually, and you will see an increase in the RPM. We are now adjusting it to 2 volts. It is relatively low speed. The important thing is that now the motor is unloaded and it isn't loaded by anything other than air resistance. How much current can we read now?
0.4 ampere approximately.
To demonstrate what we have already mentioned, that increasing current can increase the torque, we will perform a test. Firstly, I will apply some friction to slow the motor. Then, we'll use voltage to bring the speed back up to the unloaded speed value. Please increase the voltage. Now, the motor rotates at roughly the same speed. But what is the current?
We can immediately measure 2 ampere.
Yes, so you can see that when the current is high, the motor can generate a lot of torque. I think we can stop now. Thank you very much. Let's move on to the second question of today's video. We will now focus on AC-powered motors, also known as universal motors. We've probably thought a lot about electric motors that power our everyday household items, such as kitchen blenders or drills, which are powered from the wall plug. Maybe you have already heard that these appliances also contain DC motors, that is, direct current motors. How is it possible for the DC motor we have learned about to operate from AC voltage?
I have indeed thought about this question too.
To do this, let's first consider what would happen if we connected a conventional permanent magnet DC motor to the 50 Hz grid. The current in the conductor would change direction 100 times in 1 second, regardless of the position of the commutator and which winding was under voltage. As a result, the force on the conductor would also cause the rotor to try to turn in the opposite direction 100 times in 1 second. Thus, there is no constant directional rotational force, and our machine is not operating on a virtually alternating voltage supply. Like this, it certainly wouldn't work in such a case. However, if we change the polarity of the stationary magnetic field at the same time the AC current changes direction in the rotor windings, the resulting force would still point towards the same direction, allowing the motor to turn. To achieve this, we must use electromagnets in the stator instead of the permanent magnets and connect their windings in series to the rotor windings through the commutator. This way, the current changes at the same time in both the stator and the rotor, ensuring that the torque has a constant direction.
Wow, that's brilliant. It is the reason for the name universal engine.
Yes, it's sad we didn't invent this solution ourselves. Last but not least, let's see how to replace a mechanical commutator based on brush contact, which we have previously seen. If we eliminated sliding contact, the lifetime of the commutator would increase because there would be no brushes and metal dust, which would otherwise damage the coils. So this is an exciting issue to consider. Let's play with the idea of what would happen if we built our DC motor with permanent magnets on the rotor and the stator being the winding itself.
You mean turn your familiar DC motor inside out and place permanent magnets on the rotor and the stator would be wound?
Exactly as you say. In this case, mechanical commutation wasn't possible, but we could switch the coil voltages on and off with the help of electronic switches. This idea led to the development of the brushless direct current motor or brushless DC motor, also known as BLDC, which has permanent magnets on the rotor and electromagnets in the stator, with commutation done by an external control circuit. The figure shows the inside of a BLDC motor. We connect the DC voltage to the stator coils in such an order that the resulting magnetic field tries to turn the magnets of the rotor in the direction of the lines of force. But before this happens, we switch the voltage to the next coil, so that, like racing greyhounds after a rabbit, the rotor runs after the magnetic field running around without reaching it. But, in order to do this, the commutator circuit must know the current position of the rotor, or it couldn't know which coils to switch on. Therefore, BLDC motors always need a position sensor to work. The physical design of a BLDC motor can be various. You can find both outrunner and inrunner designs, meaning which part of the motor actually turns and which is bolted down to something. Where the available space is limited, a flat design is used with a disc-shaped stator and rotor placed against each other.
That sounds really good. Due to the more sophisticated design, these motors are expected to be a bit more expensive, but also more precise. To wrap up the 3 videos on this topic, let's see where and how DC motors are used. Conventional DC motors can be found in various applications such as toys, valves, robots, car electronics, or lawnmowers. BLDC motors are also commonly used in everyday life. BLDC motors drive fans and hard disks in computers, but high-power BLDC motors are also used in electric vehicles and industrial applications. As you mentioned,
A BLDC motor with a controller is, of course, more expensive than a traditional DC motor with brushes. However, its lifetime is longer, as there is no mechanical wear on brushes, no carbon dust, and its reliability and efficiency are greater as well. It can be controlled more precisely because of the lack of mechanical commutation. They are commonly used in high-speed applications where precise actuation is crucial.
Now that we finally understand how our electric locomotive and electric race car from our childhood worked, we can go and replace the disposable batteries with rechargeable ones, the remote to electronic motor control, the DC motor to a high-powered one, and design our own electric race car.
Many thanks to Bence for his encouraging words and help with the DC motor chapter. Thank you for your attention. See you again in later videos.
Thanks to Ambrus for his explanations. It was a pleasure for me to be part of the video. I wish him good work for the rest of the chapters. Remember, you can always download the curriculum in PDF format from crystalclearelectronics.eu or in Hungarian from kristálytisztaelektronika.hu. You can find a mobile application for Android and iOS platforms under the same name. Follow us on Facebook and see you soon in the next videos. Goodbye.
Bye!